Today, we're diving deep into the world of knowledge graphs. Whether you're an undergrad just bumping into this concept for the first time, or maybe a grad student trying to pick the right graph framework for your thesis, this session is going to clear things right up. We're going to break down the actual architecture of how machines understand the world, and we'll do it one connection at a time. Okay, let's dive into this. Here's our roadmap for today. First, we're defining the knowledge graph. Second, we'll look at the atomic unit, triples. Third, enforcing meaning with schemas. Fourth, core components. Fifth, some representative KGs. And finally, real-world applications. All right, jumping right into part one, defining the knowledge graph. So what exactly is it? At its core, a knowledge graph is a semantic, usually directed graph made up of entities, those are your nodes, and relations, which act as your edges. The whole point is to capture what data actually means. But I do need to issue a quick definitional health warning right out of the gate. If you dig into the academic literature, there really isn't a single universally accepted definition of a knowledge graph. It's a genuine, ongoing debate in the field. Roughly speaking, definitions tend to fall into two camps. The broad or inclusive camp says, hey, a knowledge graph is basically any large graph-structured collection of facts. But the narrow or formal camp, they argue it absolutely must have schema-level constraints and support advanced reasoning. Knowing which camp a research paper belongs to is super important, because it usually hints at the exact kind of tooling they assume you're using. Moving on to part two, let's look at the atomic unit, the triple. So most of the literature agrees that the most basic, foundational piece of a knowledge graph is called a triple. It's structured super simply: a head, a relation, and a tail. Or if you're a grammar fan, think subject, predicate, object. For example, Bill Gates, founder of Microsoft. The real beauty here is that these relationships are first-class, highly queryable structures. You aren't just dumping isolated rows into a flat spreadsheet and forcing a computer to stitch them together later with massive, heavy database joins. The connection itself is the data. And since relationships usually only flow in one direction, being the founder of a company obviously doesn't mean the company founded you, right? These are almost always modeled as directed graphs. Let's actually move to how this builds in practice. Step one, we take our triple, Bill Gates, founder of Microsoft. Step two, we introduce a second, separate fact, Microsoft, headquartered in Redmond. And then step three, a third fact, Redmond, located in Washington State. By chaining these triples together, isolated little facts suddenly transform into a continuous navigable graph. Just think about it. What kind of question can we answer now that we couldn't easily figure out from three disconnected rows in a database? Well, we can instantly ask, which U.S. state is Bill Gates' company headquartered in? A query engine can just zip right down that multi-hop path seamlessly, without any developer having to write a convoluted join that explicitly mentions Washington beforehand. It's incredibly powerful. Now for part three, enforcing meaning with schemas. This brilliantly illustrates what semantic structure actually buys you. Without a schema or an ontology in place, literally nothing stops a computer from accepting an invalid statement, like Microsoft, founder of Bill Gates. In a standard graph database, the machine just sees two nodes connected by a line, shrugs and stores it. But in ontology, that acts as a strict blueprint of constraints. It explicitly declares that the relation founder of has to start from a person and it has to point to an organization. Thanks to that one rule, an automated reasoner can look at the reverse statement, instantly realize it's totally nonsensical, and flag it as invalid. So the graph isn't just a dumb storage system anymore. It is actively enforcing meaning. Moving right along to part four, core components. Think of this as your quick cheat sheet for the 5 core elements you'll constantly see in the literature. First up, we've got nodes. These represent your entities or concepts, like a person or a city. Next are edges, which are those semantic, typically directed relationships connecting the nodes, like founded by. Third is the triple, which, as we just covered, is the minimal fact unit combining nodes and edges. Fourth is the schema, or ontology, which is that all-important blueprint of rules and constraints, like domain and range. And lastly, properties. These are just specific attributes you can slap directly onto nodes or edges, like a person's name, a date, or maybe a confidence score for a fact generated by a machine. Now let's clear up some major academic misconceptions that float around out there. A lot of folks assume a knowledge graph is just a regular database with some arrows drawn between the data points. But as we just saw, schemas actually give the data meaning, which enables true reasoning, not just basic traversal. Another huge myth, that you absolutely must use specific semantic web tech like RDF or OEL. You really don't. Property graphs like Neo4j are totally valid alternatives used all the time. Also, there's this idea that knowledge graphs have to be these massive, public, web-scale behemoths. Not true at all. Small, highly private, domain-specific graphs are just as valid. Finally, the assumption that a knowledge graph is exactly the same thing as a knowledge base, that one is heavily contested. A lot of researchers reserve the term knowledge graph strictly for graph-structured data, using knowledge base as a broader catch-all. Let's jump into part 5, representative KGs in practice. If we take a look at the historical landscape here, the year 2012 is a massive anchor point. That was when the Google Knowledge Graph launched, which, by the way, is exactly what powers those little info boxes you see on the side of your search results today. Google definitely popularized the term, but the underlying concepts go way back to earlier semantic web research. Pre-2012, they had giant projects like DBpedia, extracting structured data straight out of Wikipedia, and Freebase, which was an amazing early collaborative graph. Post-2012, we saw the explosion of things like Wikidata, which is entirely community-curated, multilingual, and actually ended up swallowing Freebase whole. We also got systems like NEL, literally learning new facts continuously by reading text on the web, and Probase, a massive taxonomic knowledge base. And finally, part 6, real-world applications and reasoning. So the absolutely crucial point here is this concept of reasoning. A true knowledge graph, especially if you're leaning into that narrow formal definition, is expected to derive completely new facts from existing ones. It pulls this off either through deductive rules, using symbolic reasoning over an ontology, or through machine learning methods like knowledge graph embeddings and link prediction. This ability to reason is the exact superpower that separates a true formal knowledge graph from a static graph database that's just sitting there holding data waiting to be queried. Because they do such a great job of integrating structured, semi-structured, and completely unstructured info into one unified format, they're just incredibly versatile. In the literature, you'll see them popping up everywhere. They are literally the backbone of modern search and information retrieval. They power question-answering systems, like the digital assistants on your phone. They run the recommendation engines deciding what you should binge watch next. We see them used constantly in educational modules and heavily in biomedicine to model super complex things like patient-drug interactions. Lately, they're even becoming absolutely essential in explainable AI, offering transparent logic paths so we can actually see how an AI reached a specific conclusion. To wrap up our explainer today, I really want to leave you, especially those of you diving into postgraduate research, with a thought-provoking question for your next seminar. Based on everything we've just uncovered about triples, schemas, and reasoning, why might a super fast-moving tech company rolling out a new social app prefer a really broad, schema-light knowledge graph, while a hospital managing clinical patient data would absolutely insist on a narrow, strict ontology-heavy graph? Think about the major trade-offs there between flexibility, speed, and the absolute necessity of enforced accuracy. Thank you so much for hanging out with me for this deep dive into knowledge graphs, and I really hope this gives you the exact foundation you need to go build some incredible structured data projects of your own.